What I want to do in this video is to give you at least a basic overview of probability and permutations. We start with probability. Probability is a word that you've probably heard a lot and you are probably a little bit familiar with it, but hopefully this video will give you a little deeper understanding. So let's say that I have a fair coin over here, and so when I talk about a fair coin, I mean that it has an equal chance of landing on one side or another. Let's say if I flip it in the air, it's not more likely to land on one side or the other. It's equally likely. It's equally likely. And so you have one side of this coin, so the crest will be the head, and then the other side, of course, the bunga raya will be the tails. And so if I were to ask you, what is really the probability? I'm going to flip a coin and I want to know what is the probability of getting heads, and I could write that like this: how to get the probability of heads. Okay, the probability of getting heads, and you probably just based on that question have a sense that what probability is asking. It's asking for some type of way of getting your hands around an event that's fundamentally random. We don't know whether it's heads or tails, but we can start to describe the chances of it being heads or tails. And we'll talk about different ways of describing them. So one way to think about it, and this is the way the probability tends to be introduced in many textbooks, as you say, well, look how many different equally likely possibilities are there. So number of number of equally likely possibilities n of the number of equally I care about the number that have the that contain my event right here. So the number of possible event that meet my condition. Sorry, I don't have space for this. Never mind. So in the case of the probability of figuring out heads here, what is the number of equally likely possibilities? What is the numbers of equally possibilities? Well, there's only two possibilities. Well, there's only two possibilities. You could only get heads or you could get tails. And what's the number of possibilities that can meet my conditions? Again, well, there's only one conditions. Okay, because the condition of heads, so only one condition. So it will be 1 over 2. So the one way to think about it is the probability of getting heads is equal to 1 over 2 is equal to half. If I wanted to write this in percentage, we know that half is equal to 50%. Now, another way to think about the conceptualized probability that will give you this exact same answer is to say, well, if I were to run the experiment of flipping a coin, so this flip is if I were to do this experiment many times, if I do it 1,000 times or 1,000,000 times or 1 billion times, and more the better, what percentage of those would give me what I care about? So the probability of getting the heads, no matter how many you get, how many you try, it will be the 50%. Actually, the larger the number that you are doing, the more likely you are going to get something really close to 50%. Now let's do another very typical example. Usually when you first learn probability, and this is the idea, always the idea of rolling a die. So here's my die over here, and you, of course, you know that they have different sides of the die. Here you can see, of course, you can see, wait, uh, 1, you can see 3, you can see 5, you can see the remaining 4, 2 and 6 on the other side. So there are 6 equally likely possibilities you could, when you roll this, you roll this, you could get a 1, a 2, a 3, a 4, a 5, or a 6, and they are all equally likely. So if I were to ask you what is the probability, given that I'm rolling a fair die, what is the probability of getting a 1? Well, what are the numbers of equally likely possibilities? Well, the number of equally possibilities to get 1 here, okay, the number of equally possibilities will be 6. And how many those meet my expectations? Our expectations is the not expectation, the condition. Our condition is only 1, so you can only see 1 once here. So one of them meets my condition, that right there. So there is a possibility of roll, there is a 1/6 of probability of rolling a 1. Then what is the probability of rolling a 1 or a 6? Well, once again there are 6 equally possibilities. Again, there are 6 probably possibility to roll 1 or 6. So there's 6 over here. So there are also 2 possibilities that will meet the conditions that I have 1 or 6. So 2 over here. This means that I could roll a 1 or I could roll a 6. So now there's 2 equally likely possibilities that meet my conditions. So there's a 1/3 probability of rolling a 1 or a 6 now. So a quick question for you, what is the probability, to get an even number of a roll dice? There are also some properties of probability. If the value of the probability is between 0 and 1, like here, it will call an event. In words, this means that the probability of an event must be a number between 0 and 1. This is inclusive. If the probability is 0, which means that it is an impossible event. Or if the probability is 1, which means that this is absolutely a certain event. And there is a types of events, which means that if the two events are mutually exclusive, if they have no sample points in common. But if I have two events are independent, when the occurrence of one does not affect the probability of the occurrence of the other. So in terms of event multiples, and event multiples occurs when two or more independent events are grouped together. Suppose we have a k independent events. So we have k independent events, and event 1 can be performed in n1 ways and event 2 in n2 ways, and so on up to even event k, which can be performed in nk ways. The number of ways that these events can be performed together is equal to n multiplied by n2 up to nk. Confused? Let's go for some of the example. So for examples, for this probability, how many sample points are in the sample space when a coin is flipped 4 times? Which means that how many sample points that we get if we flip the coins 4 times. So which means that, sorry here, so which means that if we flip 4 times of a possible event for the coins, so every coin has 2 possible ways. So 2 flip 4 times, 2, 4, 8, and 16. So you have 16 ways to get the condition, which means that probably H, probably the first one you get H, or H, T, or T, and so on and so forth. You have 16 ways of getting the different combination of this space. Or for another example, so let's say in example 7, let's change the color here, probably red. So let's say a man has 4 shirts and 7 pants. So how many different pants, shirts and pants outfits can he create? So he get, let's say, I don't know how I say, red shirts, yellow shirts, green shirts, and also blue shirts, for examples. And they have another 7 others pants that they need to combine with these shirts. So how many samples that they get? So the formula is n1 divided n times with n2. So 4 times 7, it becomes 28. So now let's talk about permutation. Permutations, let's just read these notes. Often we want to count all of the possible ways that a single set of objects can be arranged. For example, consider the letter X, Y, and Z. These letters can be arranged a number of different ways: X, Y, Z, X, Z, Y, Y, X, Z, etc., etc. This means that X, Y, Z is considered a different permutation than Z, Y, X. Each of these arrangements is a permutation. Okay, each arrangement is considered unique. Okay, and n objects can be arranged in n divided by n minus 1 many ways. Okay, this is just a formulation. So this product is called as n factorial. Okay, so let's do some calculation and example. Okay, let's do some examples here. We know that if you had 5 people, let's say 5 persons, okay, pardon me, we have 5 persons, let's say we have 5 persons, person A, person B, person C, person D, and person E. And let's say we want to put them in 5 different, let's say, positions or chairs. You have 5 different chairs. Chair number 1, chair number 2, chair number 3, chair number 4, and chair number 5. If we wanted to count the number of scenarios, or we could say the number of permutations of putting these 5 people in these 5 chairs, we could say, well, we have 5 different ways. especially if we seated people in order, which we might as well do. We could say, look, 5 different people could sit in chair 1. So for each of those scenarios, 4 different people could sit in chair number 2. Now for each of these scenarios, so we have 20 scenarios. 5 times 4 will be 5 times 4, we have 20 scenarios where we've seated seat 1s and seat 2. Next, how many people could we now sit in seat 3? Okay, for each of those 20 scenarios, well, 3 people haven't sit down yet, so there's three possibilities there. So now there's 5 times 4 times 3 scenarios for sitting the first 3 chairs. So how many people are left for seat 4? Well, 2 people haven't sat down yet, so there's 2 possibilities here. So now there is 5 times 4 times 3 times 2 scenarios of sitting the first 4 seats. And for each of these, how many possibilities are there for the 5th seats? Well, we only have 1 person hasn't sat down left, so there is 1 possibility, and so the number of permutations of sitting these 5 people in 5 chair is equals to 5 factorial. 5 factorial here, which is equals to 5 times 4 times 3 times 2 times 1 is equal to 120. Now let's do something maybe more interesting, or maybe you might find it less interesting. Okay, let's say that we still have these 5 people. We have again people A, B, C, D, and E, same people, but we don't have as many chairs as the previous one. We only have 3 chairs, 2 and 3. Okay, so not everyone is going to be able to sit down. So let's say that we only have these 3 chairs. So we have chair 1, we have chair 2, and we have chair 3. So how many ways can you have 5 people where only 3 of them are going to sit down in these 3 chairs, and we care which chair they sit in? And I encourage you to pause this video and think about this. How we can fit this situation. Oops, sorry. So let's use the same logic, but before that, let me clear this everything. Just clear clear everything up a little bit. Let's make some rooms. Okay, so we have 5% A, B, C, D, E, and you have we only have 3 chairs. Oops. So how many, if we sit them in order, we might as well. How many different people, if we haven't set anyone yet? How many different people could sit in seat 1? Well, we could have, if no one sat down yet, we have 5 here. Could have 5 different people could sit in seat 1. Well, for each of this scenario where 1 person has already sat in seat 1, how many people could sit in seat number 2. Okay, let's change the color here. Okay, well, in each of these scenarios, if one person is sat down, there's 4 people left who haven't been seated yet. So 4 people could sit in seat 2. So we have 5 times 4 scenarios where we have seated seats 1 and 2 now. Okay, finally I cleaned up a little bit. For each of those 20 scenarios, 5 times 4, how many people could sit in seat 3? Well, we haven't set 3 of the people yet, so for the each of these 20, we could put 3 different people in seat 3. So that gives us 5 times 4, 5 times 4 times 3. This is equal to 60. So there's 60 permutations of sitting 5 people in 3 chairs. To sitting 5 people in 3 chairs. Now you might say, hey, you know, when we just did 5 different people and 5 different chairs and we cared which seat they sit in, we had this 5 factorial. Remember? You know, factorial is kind of neat little operation there. Then how I can relate factorial to what we did just now? Okay, how we want to relate factorial with what we did just now? Well, it looks like we did factorial, but then we stopped. We kind of like did the factorial 5 times 4 plus times 3, and then we stopped. And we didn't go times 2 times 1 just like we did just now. So one way to think about what we just did is we just did 5 times 4 times 3 times 2 and times 1. So you could take that and you could divide by 2 times 1, and if you did that, then this 2 times 1 can be cancelled out, and with that you'll be left with 5 times, oh sorry, different change color, you can 5 times 4 times 3. And the whole reason I'm writing this way is that now I could write it in terms of factorial. I could write this as 5 factorial, the 5 times 4 times 3 times 2 times 1, and over 2 times 1 is 2 factorial. But then you might have the question, well, where did this 2 comes from? Where did this 2 come from? Well, you know, I have 3 seats, 1, 2, 3. We have 3 seats. Where did this 2 come from? Well, think about it. I multiplied 5 times 4 times 3. I kept going until I had that many seats, and then I didn't do the remainder of the seats. So the number of the thing that I left out, that was essentially the number of people minus the number of chairs. So I was trying to put 5 things in 3 places, so 5 minus 3 gave me 2 left over. So I could also write it like this. I could write it as 5 factorial, 5 factorials divided by 5 minus 3, and it is 2 factorial. And so another way of thinking about it, if we wanted to generalize, is, okay, let me clear this board first. So now it's clear. I just put it again here, so you know that the formulation they used just now is 5 minus 3 permutations, so it's equals to 5 permutation divided by 2, not factorial, sorry. So if you're trying to figure out the number of permutations, and there is a bunch of notations for writing this, if you are trying to figure out the number of permutations, so the number of permutation uh, where you could put n people in R seats, or you can put it the number of permutation where you can put n people uh, and R seats, and there's a notation as well. Well, this is just going to be n factorial over n minus R factorial. So here will be 5, and this will be 5 minus 3. So 5 factorial minus 2 factorials. Okay, the whole reason why I just showed this to you is that you could connect it with what you might see in your textbook, or what you might see in class, or when you see this type of formula somewhere else. You see that it's not coming out of some type of voodoo or bomo or something, or but I will tell you that for me personally, I never use this formula. I always reason it through, because if you just memorize the formula, you will always be with that does this formula apply here, what is n, what is r, about. But if you reason it through, it comes out straight from your logic. You don't have to memorize anything, and you don't feel like you're just memorizing without understanding. You're just using your deductive reasoning, your logic, and that's especially valuable because, as we'll see, not every scenario is going to fit so cleanly into what we did. But I just showed to you, this is what you could connect it to formula that you might see in the textbook. So you usually can use that, how to get the permutation. Like also you put in the in the lecture note, is this is the formula.